The third case is where the discriminant, gamma squared over m squared minus 4g over L, is less than 0. In that case, the square root of gamma squared over m squared minus 4g over L is imaginary. You can work out the details, but it's going to be equal to square root of 4g over L minus gamma squared over m squared. And this is just the same as this, but we've reversed the sign so that this square root is now a positive number, a real number, times the square root of negative 1. Obviously, if we multiply negative 1 times this, we get this, which equals square root of 4g over L minus gamma squared over m squared times I. And we're going to call that then omega I, where omega is just the square root of 4g divided by L minus gamma squared over m squared. By calling this omega, I anticipate the fact that we're going to have an oscillatory component to the behavior. So this is going to result in oscillatory behavior. Our solution for R is going to be R equals negative gamma over 2m, then plus or minus omega times I, so that our solution x equals a e to the RT is going to be a times e to the negative gamma over 2m plus omega I t plus b e to the negative gamma over 2m minus omega I times t. It's straightforward to use the laws of exponents to show that this solution becomes just e to the negative gamma over 2m times t multiplied by a e to the omega I t plus b e to the negative omega I t. And from what we've seen before, it's going to be easy to understand that this is just a decaying exponential multiplied by some combination of sines and cosines of omega t. The sines and cosines are going to give rise to oscillatory behavior. The exponential is going to limit the amplitude, progressively limit the amplitude, so that what we have, and I don't know if I have room to draw it here. Well, I hadn't intended to go to another clip, but it looks like I'm going to have to, and when I do, we'll discuss the behavior of this kind of solution a little bit more thoroughly than I'd originally intended.